All right, hi everybody, welcome to class. I know these circumstances are a little bit strange, but bear with me. We're in a little bit of an interesting spot here since we're a lab class. We can't really transition to online so smoothly. A lot of the stuff that we do is hands-on and involves getting in, working with the equipment, and making stuff happen in the lab. So it's been a unique challenge trying to figure out how we're going to do that online. That being said, we don't have an answer. We don't have one answer. We being me and the other lab TAs and the lab coordinators. But we are working on one right now. So we're going to be sort of taking this on a week-to-week basis, so just bear with us. I'll be giving you instructions on how we're going to do things. This is our first week in optics, so welcome to optics. We survived electricity. Hopefully you'll enjoy optics. I know I do. It's a pretty fun topic. Unfortunately, you don't get to play with the lasers and the lenses and stuff like that, which is usually pretty fun, but I'm going to do my best to convey that information to you so you can fill out the lab. Okay, so that's a little bit about class structure. Basically though, that's going to be our structure of the class for now. I can't guarantee that each week I'll have a demonstration for you or something, but I'm going to do my best. So just bear with me and I'll keep you all updated. Now obviously I'm not going to grade this incredibly hard since we're in such strange circumstances, and please, if anything at all comes up, like just communicate with me. I'm very willing to compromise and make adjustments and stuff like that. I know we're all in a really weird situation, so I hope you all are staying safe, staying healthy, staying self-quarantined. Hopefully you're at least opening a window or going for a walk away from people so that you get a little bit of fresh air and some sunshine so you don't lose your sanity. All right, so first we're going to be talking about Snell's law. Now, Snell's law is the equation that governs how light bends when it goes through different media, different materials. So the first thing I want you to imagine is that we've got some light ray coming in like this, right? So this is my light coming down, like maybe I'm shining a laser or a flashlight, and there's some material right here. So this is going to be like some big chunk of, like, let's say glass. This now light gets refracted in any material, but we're going to use glass in this example, any transparent material really. So imagine our light's coming in. Now we know light always moves in a straight line, and you've probably heard that light always moves at the speed of light. Well, that is true and a little bit of a misnomer, because the speed of light in vacuum, i.e. when the light is moving through empty space with nothing else around, that's what we usually take to be the speed of light. That's what we call c. That's about 3 times 10 to the 8 meters per second. That is the speed of light. That's the cosmic speed limit, as it were. We say nothing can go faster than that. But when light is moving through a material, it actually gets slowed down a little bit. And that's sort of the basis for this whole phenomena of light bending when it enters different materials. So when the light actually enters this material, it's going to bend. And what I mean by that is if I draw a line here that is perpendicular to the surface, right? This is a 90-degree angle right here. When this light enters, and let me extend my perpendicular line down like this. When this light enters, instead of continuing in a straight line through, it actually gets bent a little bit closer to this horizontal here, or to this perpendicular, excuse me, to the normal. Now what I'm saying basically is that the angle right here, let's call this theta incident. This angle is actually bigger than this angle, theta reflected. Let me write that a little bit bigger, make sure you can see it. Call this angle theta sub r for reflected. Now in this case, it doesn't have to be that the incident angle is bigger than the reflected angle. That's actually governed by some stuff I'm going to talk about in a little bit. But right now I'm assuming that this material outside of here is air, and this material inside here is glass. Okay, so air is really not super dense, and so we can really, it's really close to being a vacuum, and so we say that light actually moves at the speed of light in air. And I'm going to add a little bit of formalism to that in just a sec. But for now, air into glass, we know that this incident angle, theta sub I, is greater than this angle, theta sub r, down here, which means the light actually got bent, so it came in like this, and it got bent, and is continuing down this way. So that's what we mean when we say light bends when it enters a material. So now that we've discussed that light actually slows down when it enters another material, and that results in the ray being bent a little bit closer to the normal here, we're ready to write down Snell's law. So I'm not going to derive this for you. It's a pretty interesting derivation, but this is one of the most famous results in classical optics. It says that it relates the incident angle, the refracted angle, and the index of refraction of these two. Now, the index of refraction of a material is basically a measure of how the speed of light changes in that material. Okay, so the index of refraction of air, we use n for index of refraction. The index of refraction of air is about 1. And this means that the speed of light doesn't change when it's in air, basically. And now, in glass, the n, the index of refraction, is about 1.5 for typical glass. So this means that the speed of light is reduced a little bit. Okay, so now that we know these two things, we can write down Snell's law. So Snell's law says that the incident angle, the sine of the incident angle, multiplied by the index of refraction incident, so I'll just mark these with incident and refracted. So n sub I times sine of theta I equals n sub r, the index of refraction of the second medium, sine of that angle, theta r. So this basically just tells us how the incident material and angle relate to the refracted material and angle. And we're going to go ahead and use this relationship in a couple different ways today. All right, the last thing that I would like to point out is that when light comes in here, anytime it crosses a barrier, right, where the index of refraction changes, there's actually a little bit of the light that gets reflected. So when I say refracted, I mean that's the light that's coming through and has gone into the glass. But there's actually a little bit of light that also gets reflected back out this way. So this is the reflected light. And this right here, this is the refracted light. All right, now it's important to keep those two straight. So the reflected light comes back out at the same angle it went in at. So that's basically just like this surface is kind of acting as a mirror. The refracted light comes out at an angle that's given by this relationship right here. It depends on the index of refractions of the material and the other material and the incident angle. Okay, so that's how light behaves when it enters a different medium. Now, you've probably experienced this more than you might realize. Anytime this happens, light passing through a window, through glasses, anytime this an index of refraction change occurs, you see this phenomena happen. This phenomena works both directions. So if we let this light continue through here, this refracted light, if we let this continue all the way down till it hits this surface, I draw my normal lines here, the same thing is going to happen, except now we have a new angle of incidence, which is the same as the old angle of refraction. So this is my new angle of incidence. I'll just go ahead and leave that out for now. This is my new angle of incidence. And there's going to be a new refracted angle, and it's going to get bigger this time because it's coming from an index of refraction that is higher, going to an index of refraction that's lower. Remember, this air exists out here too.